everyone, welcome to the course on medical biomaterials. We will continue on the topic of polymers. Okay. We were looking at many properties, and thermal properties of polymers are also very important, because polymers, the amorphous region of polymers sometimes exhibit glassy state and then sometimes they exhibit rubbery state, okay, the amorphous region. Okay. So, at certain temperatures, that is at lower temperature, the molecules of polymer vibrate but not move significantly. So, they almost look like glass, okay, that is why it is called glassy state. That means they become brittle, hard and rigid. When the temperature is raised, the polymer, the amorphous region of the polymer becomes a rubbery state. That means they become soft and flexible, name implies, right, like rubber. So, the chains wiggle, so they become like soft and flexible like rubber. So, the glassy state, rubbery state, that is a very important point, and that is known as the glass transition temperature, Tg. Tg is the glass transition temperature, and above which it becomes a rubbery state and below which it will be a glassy state. As I mentioned, it is valid only for the amorphous region. It depends on the molecular weight of the polymer, rate of heating or cooling, what type of measurement method I use, and so on. Okay. So, then melting point, the crystalline portion of the polymer at some temperature starts melting, that is also very important to know. So, just like Tg, okay, the glass transition temperature, the melting temperature, maybe 200 degrees or 300 degrees. Of course, in biomaterial inside the body you are not going to face such very high temperature, but still it is good to know what is the melting temperature of the polymer. That is a property of the crystalline region. So, if the polymer is very crystalline, you will see very sharp melting temperature. If it is very amorphous, you will not see. So, a long time back I introduced this instrument called differential scanning calorimeter or calorimetry, DSC. It can be used to measure all these properties. Okay. So, what is so important about this temperature? The temperature determines the volume of the polymer, dynamic mechanical properties of the polymer, and so on. For example, if you look at crystalline solid, okay, the temperature as increase, okay, and it occupies more volume. Semi-crystalline solid, you will see this is called the Tg. Okay. Similarly, for glassy solids you will have like this is the Tg. But the dynamic mechanical properties also start going down. Okay. You can see this. So, semi-crystalline, cross-linked. So, as the temperature is increased, the E, okay, modulus can also start decreasing. Okay. So, that is why temperature is very important. So, that is why we need to understand these Tg and Tm. Tm is the melting temperature. So, the Tg, when the polymer is cooled below this temperature, it becomes hard like glass. When it is heated above this temperature, it becomes rubbery, okay, like rubber. And generally the heat flow was plotted against temperature when you use a DSC. So, it looks like this. Okay. So, there is a big I mean, this is called the phase change, and this temperature that is in the middle of this is called the Tg. Okay. So, hard plastics like polystyrene, polymethyl methacrylate, okay, are generally used below their Tg, so that it looks like a, that is Tg greater than 100, the Tg is greater than 100. So, it is used below their Tg, so that it looks like a glassy material. Whereas, if you look at rubber elastomers like polyisoprene, polyisobutylene, you need to use them above their Tgs. That means they will look like a rubber, soft and flexible. So, if I am using rubbers, I would like to use it above their Tg, and if they am using polystyrene or PMMA, I will use okay, below their Tg, so that they look hard. Okay. So, this table gives you Tg of many polymers. This is taken from this reference. As you can see, some of them have Tg below their room temperature. If you take 30 as our room temperature, polyvinyl acetate, PHB, polyhydroxybutyrate, this is a polymer produced by bacteria, polypropylene, okay, polyvinyl fluoride, polyvinylidene fluoride, rubber, they have very low TGs, okay, as you can see below there room temperature. Whereas if you look at other like acrylonitrile butadiene, polycarbonate, polymethyl methacrylate, polyvinyl alcohol, polyvinyl chloride, polyamides, PET, polyesters, polyethylene terephthalate, polystyrene, polysulfone, PTFE, polytetrafluoroethylene, they have TG above room temperature, above 30 degrees centigrade. Okay. So, there is lot of difference between the TGs, as the name implies. When you above the TG it becomes like a soft rubbery, below the TG it becomes hard and brittle like your glass. Okay. So, you can measure TG using a DSC, the phase change it can be nicely seen in the DSC. Okay. Polymer blends, the beauty of polymers is we can blend different polymers to achieve the required mechanical properties, required softening, required TGs and so on actually. So, physical mixture of 2 or more polymers with or without any chemical bonding. Okay. So, if I am going to have 2 or more polymers and I put a chemical bonding, that can be called cross linked. Okay. We use cross linking agents like glutaraldehyde, whereas if I have just physical mixture I will not have any reaction cross linking. Okay. So, they are called homogeneous or they are called heterogeneous. Heterogeneous will be immiscible, homogeneous will be miscible on molecular level. Okay. So, when we blend it nicely, interfacial tension between the polymer phases approaches 0, large interfacial tension, that means they can have a phase separation, low critical solution temperature, that means low critical solution temperature. So, the phase separation of a miscible blend during heating, upper critical solution temperature, phase separation of a miscible blend during cooling. Okay. So, this is during heating, okay, as you can see here, and this is during cooling. So, this region you will have a single phase, okay, whereas above in this region and in this region you will have 2 phases. So, ideally if I want to have 2 polymers well blended mixed very well, then I would like to have them in a single phase. So, I need to operate in this region of temperature. Okay. So, we can get this type of graph where you have the y axis is temperature, x axis is composition. So, I mix them together and in this region of temperature they will be in single phase, whereas if it goes here or here, this is the low critical solution temperature, okay, during the heating phase, and this is during cooling phase, okay, where we will have the 2 phase separation taking place. So, I would like to work in this region. So, suppose if my room temperature is 30 degrees here, okay, I need to select the concentrations so that I am in the single phase region. So, we need to understand what is the mixing behavior of 2 polymers, so that do they form single phase or do they form 2 phases. Okay. So, advantages of this type of blend: easy to prepare, cost effective, properties can be manipulated, that is the beauty of it. We can blend nylon and urethane. Okay. So, for example, urethane is like rubber, nylon is okay, very strong. So, we can achieve both by mixing, and generally blend properties will be superior to the individual properties. So, we can achieve advantages of both the polymers into this blend. Okay. Some examples: PVC, it has got poor impact resistance, it is brittle, okay, it can break. So, what do? They add ethylene vinyl acetate copolymer. Okay. So, improved toughness and impact. So, it will not be brittle, some flexibility is there, that is why it is used in medical films, blood bags. So, PVC alone if you use, it is very brittle, it is not flexible. So, they add ethylene vinyl acetate copolymer, okay, of this. So, it can be used for bed bags or films or tubings and so on. Polyesters, okay, shrinks, they have problems with dimensions, maintaining their dimensions. So, when you add polycarbonate, it gives you good stability, it reduces shrinkage, again it is used in blood therapy, drug delivery, intravenous kits, components, flexible medical tubing, surgical instruments, because polycarbonate is very tough. Okay. It is called an engineering plastic, so it can be used for strong applications, surgical. Acrylonitrile butadiene styrene, this is like a rubber. Okay. It is low heat distortion temperature. So, they add polycarbonate. Polycarbonate has very good temperature resistance. So, of course, then we can use it for housing of material, surgical instruments, diagnostic devices, drug delivery, and so on actually. Okay. So, polycarbonate I was talking about. So, this is the structure of polycarbonate. This is the repeating unit of polycarbonate. Okay. How is it made? Diphenyl carbonate, that is here, diphenyl carbonate, okay, and bisphenol A. That is how you make diphenyl carbonate and bisphenol A. It gives you polycarbonate and it gives you phenol. Okay. It is called an engineering plastic, temperature resistance, impact resistance, and transparent, can undergo large deformations without cracking or breaking. It is used in heart lung assist devices, coating of contact lenses. Okay. So, polycarbonate is it is almost like glass, you can see through. So, it is used in some of those applications, okay, coating on contact lenses and so on actually. It is also used for high impact strong medical devices. Another polymer which I mentioned just now, polyurethane, this is like rubber. Okay. This is the polyurethane. Okay. It is a condensation of di or polyisocyanate with the polyol. Polyol is a alcohol. When I say polyol, it is an alcohol here. This portion is polyol, this is the isocyanate here. See, this is isocyanate bond, this is the polyalcohol bond. So, it is a soft elastomeric applications used for foams, encapsulating hollow fiber devices, deep molded gloves, balloons, asymmetric membranes, functional coatings, extrusion for catheters, artificial heart, pacemaker lead, even urethral stents and so on. So, polyurethane, this is very soft elastomer, polycarbonate very hard engineering plastics. Okay. So, let us look at a problem. Ultra high molecular weight polyethylene is used in knee or hip joint prosthesis. Okay. Its molecular weight is 2 into 10 power 6 gram per mole, and because it is polyethylene, it has got only CH2 as repeating. So, it has got say CH2 as repeating. Now, calculate the number of these repeat units. How do you do that? It is quite simple. Weight of one repeat unit. So, it has got 2 carbons into 12, 12 is the atomic weight, and then it has got 4 hydrogen, 4. So, 2 into 12 is 24 plus 4 is 28. So, how do we calculate number of repeat units? Its molecular weight is 2 into 10 power 6, okay, divided by 28, that will give you 71,428 this repeat units. Okay. Now, calculate Mn, that is the number average molecular weight if polydispersity is 1.5. So, the weight average is this. I mentioned before that weight by number average is equal to the polydispersity 1.5. So, it is quite straightforward. So, polydispersity is 2 into 10 power 6 divided by 1.5, that is 1.33 into 10 power 6. Third part, calculate the length of a stretched chain. Okay. So, this polyethylene ultra high molecular weight polyethylene, it occupies a tetrahedral structure. So, the C bond length of 0.126. Okay. We have 3 carbons as the repeat unit. So, we need to calculate the mass of that, which is 3 into 12 plus 1 into 6. So, we have the molecular weight as 2 10 power 6 and divided by 42. So, that leads to 47,619 as the repeat units, and if you multiply that with the 0.126, we get 6000 nanometers, which is 6 microns. Okay. So, look at it, polyethylene, it forms a tetrahedral, whereas if you look at polytetrafluoroethylene, which is there are no hydrogens, only fluorine, fluorine, fluorine. So, you have CF2, CF2, CF2 connected together, it forms a rhombohedral, whereas polyethylene which has got CH2, CH2, it forms a tetrahedral. So, these are fluorine atoms. Okay. A 15 repeat unit of PTFE has a hexagonal structure with the A that is the side of the hexagon 5.65 angstroms, and C that is the height of the hexagonal structure 19.5. Calculate its theoretical density. Okay. So, mass 15 into 12 is the carbon, okay. F2 CF2, right. Fluorine is 19 into 2 divided by 6.023 into 10 power 23, that is the Avogadro number. So, when we do this calculation 1.25 into 10 power minus 25 gram per mole. Why do we do this? 15 repeat units, and each repeat unit has CF2, CF2 and so on, right. C is the carbon, 12 F2, that is why 2 into fluorine, okay, divided by the Avogadro number, that gives you the mass of this 15 repeat unit in mole per mole. Now, the volume of an hexagon, square root of 3 divided by 2 A square C. A square is 5.65 square, C is 19.5. So, that comes out to be this Cc per mole. So, mass by mole density is 2.31 gram per Cc. Okay. Okay. So, composites, what is this composites? So, we can have a combination of microscopic scale of 2 or more materials, okay, which have general physical properties. So, I can put in glass beads in polymers, I can put in carbon fibers into the polymers. Okay. You must have heard about fiber reinforced plastics, you must have heard about carbon reinforced plastics. Okay. So, we can have very fine carbon particles put into some polymers, we can even put fibers into polymethyl methacrylates. So, that adds to the tensile strength. Okay. So, we can tailor depending upon the specific application. For example, boat parts are made of fiber reinforced PMMA, and they are extremely strong. These fibers, when they are aligned in certain direction, it adds quite a lot to the tensile strength. Similarly, we can have glass beads or even carbon mixed with polymer to make these composites, and that adds quite a lot of strength, mechanical properties to the polymer. Okay. So, polymer ceramic composites, for example, collagen hydroxyapatite. Collagen is a polymer, hydroxyapatite is an inorganic material. So, they add to each other and they give a lot of strength. They are used in dental and bone applications. Okay. Polymer, it will promote cell growth, the ceramic is bioactive. Polymer can degrade without leaving any foreign substance, whereas the ceramic is not going to be degrading. They may be helping in osteoconductive, osteoinductive properties. Okay. So, by adding this, you can see the advantages of both are taken in. The ceramic could be bioactive, they be osteoconductive, osteoinductive. Polymers do not have that property, but polymers can promote cell growth, they can also degrade without leaving any foreign substance over a long period of time. So, we can nicely use them for tissue engineering purposes, growth purposes. Of course, polymers do not have good mechanical properties, and they are also not bioactive, that is taken care by these ceramic. Ceramics are brittle, so they cannot take over load bearing applications, whereas polymers are much better than these ceramics. So, this is a very good example of polymer ceramic complex, and a lot of dental bone applications have this type of combinations. So, polymers are reinforced with inorganic, it could be calcium sulphate, alumina, hydroxyapatite. After all, your bone is a polymer ceramic composite, right. They can give better cell response, they will have very good mechanical properties, improved tissue integration. So, this type of combination also has some usefulness and advantages. Few examples of polymer ceramic: type 1 collagen, combined with hydroxyapatite or tricalcium phosphate. They can be used for long bone fractures, traumatic osseous defects, bone void fillers. So, in a bone void sometimes we can fill it up only with the inorganic material, but then they could be brittle. So, we add collagen to that. Similarly, type 1 collagen or chondroitin 6 sulfate with hydroxyapatite. This is used in dental, periodontal effects, prosthetic osseous reconstruction, maxillofacial reconstructive surgery. After a trauma, the facial reconstruction, we can combine this type of composites. Fibrin biphasic calcium phosphate, again bone void filler. Collagen tricalcium phosphate, filling, bridging, reconstruction, okay, and bone fusion. Collagen magnesium enriched hydroxyapatite nanocrystals. Okay. So, magnesium is also bioresorbable. Okay. So, we can think about long bone fractures, hip arthroplasty to fill actobular defects. So, you see we can use calcium tricalcium phosphates, we can use hydroxyapatates, okay, calcium phosphates with collagen generally for bone applications, filling up of voids, long bone segmental defects, and also for dental orthodontic applications, because your inorganic material cannot bear loads. So, we need collagen, but the beauty of the inorganic material is they are osteoconductive, osteointegrative. So, we can use them. So, this type of combinations are very advantageous, each helping each another. Okay, let us look at one simple problem related to these composites. Look at this, finely ground silica, that is a density, is used as a filler for polydimethoxysiloxane, which has a density of 0.9. Okay, this is a polymer, this is the structure of this polymer, dimethoxysiloxane, silica is there, oh, that is why it is called siloxane. It is optically clear, inert, non-toxic, good flow properties, non-flammable. It is used quite a lot in cosmetic, consumer product industry, it is used as filler in breast implants. So, because of its clarity, it is used widely in cosmetic. Okay. That is this. Now, question is, I am mixing silica with PDMS. So, what volume fraction of silica is needed to make this silastic rubber, because PDMS is very rubbery, to achieve a density of 1.25. So, we have a silica density 2.65, siloxane, that the polymer PDMS density 0.9. So, I want to achieve this density of 1.25. What should be the volume fraction of silica I need to add? Okay. So, same thing, what volume fraction of silica is required to make the silastic rubber with density of this. This problem was taken from this reference book. Okay. So, what do we do? It is called a mixture rule, that is the density of the composite, density of component 1, the volume fraction of component 1, density of component 2, volume fraction. So, I want to achieve 1.25, silica is 2.65, siloxane is 0.9. Okay. So, what should be the volume fraction of silica? Now, this fraction and this fraction is equal to 1, that everybody knows, right. So, V PDMS we can put 1 minus V silica. So, from that we can calculate volume fraction of silica. Volume fraction of silica is 0.2. So, I need 0.2 volume fraction or 20% silica to achieve a density of 1.25 for the composite. Okay. When I say 20% silica, the 80% is this polymer PDMS. Interesting problem. What is the weight percent of silica? Okay. So, this is volume fraction. So, I need to calculate the weight percent, that is also very simple. Okay. Weight of 1 cc of rubber is 1.25 grams. Okay. And the volume fraction is 0.2. Okay. So, volume fraction is 0.2, weight is this much. So, we can calculate 0.2 into 2.65 divided by 1.25, 2.65 divided by 1.25, okay, that gives you 0.42. So, I need to add 42% by weight of silica, whereas I need to add 20% by volume of silica. Why 42%? Because density of silica is very high, that is why weight wise it is very high. Okay. An isotropic composite which contains spherical silica particles, the modulus is 72 gigapascal in a polymer which is 1 gigapascal. Now, I am adding this 33% by volume of this into the polymer. What is the modulus of the composite? Okay. So, there are some equations available in literature. One equation is this, Gibson and Ashby, especially for dilute material, spherical material, if you add and achieve an isotropic composite, this is the equation that is given. E, that is modulus of this composite, 1 plus 5 EI, that is the inclusion material which you are going to add, and this is the M of the polymer, the VI is the volume fraction divided by 3 plus 2 EI by EM. EI is the inclusion material you are adding, EM is the polymer material. This is taken from this reference. So, we just have to substitute 5, 72 minus 1, 33% here, 3 plus 2, again 72 by 1, that gives you 1.8 gigapascal. That is the modulus of this particular composite when you have 33% of silica and rest is the polymer, 33% by volume. Now, long time back I mentioned about Roy's model, right. Okay, this is the Roy's model where the E, that is the modulus, is given by 1 divided by 1 divided by 1 divided by 0.33, that is the volume fraction, divided by 72 plus 0.67 is the volume fraction of the polymer divided by 1, that gives you 1.5 gigapascal. So, some difference you can see. So, depending upon the type of model which we use, we can get slightly difference in the number of the composites. Okay. So, let us look at another problem. Average bond energy of carbon chlorine in PVC, as you know, polyvinyl chloride, it contains a lot of chlorine. The bond energy of this CCl is 340 kilojoule per mole. Now, can visible light which has got a lambda of 4000 to 7000 angstrom have enough energy to break the bond? So, we need to calculate whether the energy is greater than 340 so that it can break the bond. Okay. This can happen especially when I have biomaterial and which is made up of PVC, and I am trying to sterilize it using UV radiation. Will the bonds get broken? I need to do that. So, from with respect to that, this is a very important problem. So, what do we do? You remember this equation, E is equal to Hc by lambda. Okay. H is your Planck's constant, C is the wavelength, the light, okay, the speed of light, lambda is this, okay, that is the wavelength. So, C is the speed of light, lambda is the wavelength, H is the Planck constant that gives you energy. Planck constant is given by 6.626 10 power minus 34 joule second, C is the speed of light, so many meter per second, okay. That is 3 into 10 power 10 centimeter per second. Lambda, let us take the smallest 4000 angstrom, that is 4000 10 power minus 8 centimeter. Avogadro number is 6.023 10 power 23. So, energy per mole 6.023 into 10 power 23, 6.626 10 power minus 34, C is 3 into 10 power raised to the power 10 divided by lambda 4000 minus 8. So, that gives you 299,000 joule or 299 kilojoule, so per mole. So, which is not enough, okay. Average bond energy is 340. So, I need to achieve 340, but I got only 299. So, if I am using a light whose wavelength is 4000 to 7000, then I will not break the Cl bond, whereas the lambda is going to be much less than this 4000. Okay. For example, if another 30 or 40% less, then this number may go up 30 or 40%. Okay. So, I may come very close to this, and chances are I may be breaking the bond of C and Cl. Okay. This is a very interesting problem. So, if I am using visible light of wavelength 4000, then I will not be breaking this Cl, but if I am going down say maybe 3000 or less, then the bond between C and Cl can break. Okay. So, this is also another very interesting problem worth pondering about. So, we did quite a lot of in the past 3 lectures on polymers, looked at different types of polymers, applications of polymers in different areas of biomaterial and implants, then some properties of polymers, and also we looked at a few simple problems which gives you some idea about polymer and their application area. Thank you very much for your time.